Okay, so I'll be talking about black hole complementarity and trying to connect some more dots. I guess I should mention this is based on some recent work with Laurus Thorlacius and some earlier work with him and Klaus Larjo. Okay, so I'll begin with just a brief discussion of effective field theory and try and clear up some of these issues about measurements and their relation to correlation functions and effective field theory. And I'll argue it's conventional on the outside and rather fuzzy on the inside. So an idea that's compatible with black hole complementarity and also very similar to what the fuzzball people are saying. I'll then talk about local observables near the horizon. And one of the things I'll argue is firewalls are a generic firewall is going to be visible from the outside. And I'll show that by thinking about scalars in a Schwarzschild background and just explicitly computing a one-point function that illustrates that. And I'll try and set that calculation up in a way that you can promote it to see what's going to happen if we look at generic pure state black holes. And we'll see what happens there. And I'll end with some comments somewhat related to some of the things Eric and Herman were talking about yesterday. Okay, so let me begin by just giving a brief review of how we think about measurements in quantum field theory. So quantum field theory gives us some set of correlators, and I want to talk about the physical meaning of these correlators. So usually when we compute a correlator of a couple of fields, we have in mind that we're actually coupling those fields to some large measuring apparatus and projecting the field into some kind of eigenstate, for example, of momentum. So that's what LHC detectors do, for example. And if you want to do this in a very mathematically precise way, you only have a shot at doing this ad infinity. Okay, so if we want to think about doing it near a black hole, I mean, it'll still work well as long as we stay several Schwarzschild radii away. If we want to have a big detector closer than that, then we have to worry about trying to support it there and all the acceleration radiation that is going to create. And it starts to get rather murky what we're actually measuring in that kind of situation. So the relation between this notion of measurement and the correlation functions that our theory is presumably providing us with becomes progressively murky as we get close to the horizon. And once we go inside the horizon, all bets are off for some kind of mathematically precise relation between correlators and measurements. So yeah, so I'm imagining we have some kind of microscopic theory that gives us some complete set of microscopic correlators. Then our challenge is to interpret those in terms of what people see at different points in the space-time.
But doesn't this depend on whether you are static or whether you fall? If you go just in inertial motion towards the black hole, even if it's 2 MOA, if it's a very big black hole,
yeah,
there's nothing you need to support. You just go in, and locally everything looks like Minkowski space. Well, it's still pretty low curvature space. So why would there be any problem with effective field theory correlators?
Well, maybe I should continue with this discussion, which will kind of address that. So yeah, if we're freely falling very close to the horizon, we only have a proper time of order m to live. So we have a limit to the kinds of energies we can resolve. So the kind of measurements we do and the very precise correlators our microscopic description might give us are no longer related in some kind of very precise way. So the observables that we measure start to acquire some kind of fuzzy nature.
David, this is really a question of relative scales, right?
That's right.
There's the conventional story that planet Earth could have just crossed the horizon of a huge black hole, and we're making measurements.
That's one of the points I'm going to make. Yeah.
Yeah, you could have something that's quite sharp. And that's it.
Anyway, so because of this fuzzy nature, there's a potential for non-locality in correlators that is invisible to the observables. Again, it's a question of scales, and that's really what it comes down to. But this is one scale that you're not going to get away from once you're inside the horizon. Okay, so when correlation functions in the bulk are local, we can view some kind of local effective field theory as essentially just a summary of this set of correlators. So black hole complementarity suggests we can always use some kind of local effective field theory outside the stretched horizon of the black hole. And again, the fuzzball picture is compatible with that kind of idea. If we want to use effective field theory inside the horizon, essentially what we have to do is take our exact correlators that might represent observables inside the horizon, and according to black hole complementarity, they will not behave in a local way with respect to the guys that we've set up outside. But we can try and throw away the non-local part of those correlators and define some kind of inside effective field theory that's still local and unitary, but we've truncated the correlators. So it's now only some kind of approximate description of the true underlying dynamics. So localized observers will still find some kind of local unitary description that's predictive, which I think is the kind of thing some of the comments were getting at. But it will not agree with the exact effective field theory outside. Okay, so if we want to construct an effective field theory, we can do it for different patches of the space-time in general. We can be very successful in making predictions with these unitary effective field theories. But when we try and relate them to our fundamental underlying microscopic description, we have to worry about the fact that in general, they're only some approximate description of what's going on. And they may not all patch together in such a way that your global effective field theory is local. Okay, so let me now turn and talk about pure states and complementarity. So I'd like to avoid in this talk having to talk about the interior of the black hole. We heard a lot about that yesterday. And I guess my point of view would be that this interior description is going to be highly dependent on your underlying quantum theory. So what I'd like to try and do for today is just focus on some universal questions that one can ask outside the stretched horizon of a black hole, where at least most of us would agree there's some kind of local unitary effective field theory that goes all the way
David,
out to infinity.
Let me ask a quick question about the interior since it's my last chance. Is that statement supposed to mean that you think that the degree to which effective field theory is valid for the infalling observer is highly dependent on the underlying quantum model and sort of not predictable in advance?
Well, if the infalling observer is outside the horizon but infalling,
I mean once they cross the horizon.
After they cross.
After they cross. Or maybe you're just declaring that you don't know and don't want to deal with that problem. I wanted to understand.
I think we heard a lot about it yesterday, so that will be my answer. But yeah, it's something I'd like to think about more in the future. But so there have been a lot of, I guess, retreat from the fact that there's maybe a sign of the firewall outside, but I'd like to argue that that is in fact not the case, and just think about computing the expectation value of some scalar stress energy tensor in the Schwarzschild background. Okay, so just a free scalar field coupled to gravity. Okay, so let me just review some old facts from the 1970s. There were various competing vacuums at that time. And one that's quite relevant for the discussion is known as the Boole-Ware vacuum. So that's the vacuum state where we just use Schwarzschild time to decide whether modes have positive frequency. And we do that for the ingoing modes and the outgoing modes as well. So as Lenny told us yesterday, Schwarzschild time doesn't allow us to cross the horizon. So this gives us a model for states where you might have perhaps a mirror boundary condition near the horizon, or perhaps even a generic membrane. And what you find is not some kind of small stress energy near the horizon. You find a genuine power law divergence on both the past and the future horizon. And I'll go into the details of that a little more in a moment. More popular vacuum here is the Hartle-Hawking vacuum. In this case, we use Kruskal time on the past horizon to distinguish our positive frequency outgoing modes, and the Kruskal coordinate on the future horizon to distinguish the positive frequency ingoing modes. So if we use that definition of the vacuum state, we find a stress energy that's smooth on both the past and the future horizons. Now, the surprising thing that came out of that was that if you then look at the stress tensor at infinity, you find you're not only getting Hawking radiation coming out, you're having to send it in. Whereas in the Boole-Ware vacuum, no radiation goes in and no radiation comes out. Okay, so that's good for thinking about a black hole in thermal equilibrium. Now, maybe the most important vacuum for the present set of discussions is the Unruh vacuum. This is a kind of mixture of the two. So for the ingoing modes, we use Schwarzschild time to set up positive frequency modes. And for the outgoing modes, we use the Kruskal time on the past horizon. Okay, so we do our computation and find that the stress energy is smooth on the future horizon. But like the Boole-Ware vacuum, there's a power law divergence on the past horizon. And that's maybe something people should watch out for when thinking about these double CFTs. Any generic infalling state from the right is going to give you a singular past horizon if you're worried about that. Okay, but this gives us a good model for black holes formed in collapse. We can actually generalize this to arbitrary infalling states, and the stress tensor will stay smooth on the future horizon. So let's look at this in a little more detail, and I'll use some results by Candelas from the early 1980s. And to simplify things, I'll just look at the expectation value of phi squared to save writing a lot of indices. And since it's a free scalar field, you can always take derivatives of this to construct the stress energy tensor and contract it with some unit normal time-like geodesics to get the energy density seen by some freely falling infalling observer. Okay, so I kind of like this formula. It reminds me of the ultraviolet catastrophe formula in black body radiation. And we can see most of the features just by kind of eyeballing it. So in particular, these R's are some complicated radial functions, but this is reflecting the fact that in this Unruh vacuum, we have a thermal distribution of outgoing modes. Okay, so if we do these derivatives and look at the limit of this on the future horizon, there's going to be a lot of divergences coming from the limit where R goes to 2m. So these two terms here are renormalization counter terms that are coming when you do the proper renormalization of this operator. And there's a delicate cancellation as R goes to 2m between this term and these terms. Okay, so it only works if you have this exactly thermal, essentially only works if you have this exactly thermal function here. On the other hand, if we look at this term in the limit that R goes to 2m, it's just finite. So we could have whatever ingoing modes we want and get in principle, we could easily generalize this expression to have whatever ingoing modes we want here, and it won't change the divergence properties of phi squared. Okay, so we have a lot of freedom in what we can send in, but if we try to do any kind of projection on what's coming out and change that purely thermal state coming out, we will immediately see a divergence on the outside the stretched horizon. Okay, and if we do Hartle-Hawking, we get another cotange factor here. So in that case, even if we went to the past horizon, we would have a smooth expectation value of T mu nu. So in the past horizon, the roles of these two terms essentially swap. And for the Boole-Ware vacuum, neither of these terms has a thermal factor in front of it and is divergent both on the past and the future horizons. Yeah.
Yeah, I'd just like to understand. So you mentioned that a renormalization. Did you mean normal ordering, or what actually is the prescription that determines the counter terms? Normally, I guess we would normal order, but in this case, if I subtract the vacuum you're computing a vacuum expectation value, so normal ordering has all kinds of ambiguity at this level.
Yeah.
What's
so
the prescription that gives you a unique answer here?
Yeah, Candelas used point splitting regularization.
Okay.
I don't want to.
Yeah.
It's a very messy calculation.
It's a but he had a certain canonical form for the short distance divergence that he that he wanted to subtract. Which one can think of as being
as a gravitational counter term.
The condition is that the infalling observer doesn't see anything singular there. That's the prescription, I think, that he was just asking about. Just think about this in the Rindler-Minkowski case. It's the condition that that you're in something like the Minkowski vacuum, where you sail across the horizon without encountering a singularity.
I think that's how you pick the vacuum, but that's not how you choose your normalization scheme.
No, well, okay. So he was asking about
the
prescription.
I think maybe I can get the answer myself. So you take a local Minkowski metric. You take the inertial Minkowski metric, and that's the one relative to which you normal order. I guess that's
yeah. I think that's basically another way to say it.
Yeah, you can probably reinterpret it that way. Okay. Good. So if we replace this outgoing mode distribution by any kind of non-thermal probability distribution, we get a naked firewall. So a couple of examples. We could imagine changing things so we have some eigenstate of the number operator of the outgoing radiation field. So instead of that thermal factor we just saw, we might imagine replacing that by some of your favorite delta function frequencies. And by the argument I just gave, by this formula, you're going to get a divergence well outside the horizon if you do that. So we're seeing there are genuine divergences that appear mode by mode. So if you get rid of a single mode, there's going to be some divergence left over from that counter term. Okay. And likewise, if you replaced your stretched horizon by perhaps a mirror or some kind of hot membrane, again, that would be like going to the Boole-Ware vacuum and replacing that thermal factor by unity, and you would get a divergence. So typically, your infalling observer crossing, say, a radius r where the fiducial temperature is T, even your infalling observer would see something of order a temperature T in that situation. Okay, so a very serious naked firewall.
Just one question about the previous slide. Maybe you're going to come to this, but the firewalls, I think that Don and Joe and AMPSS have been talking about a very conservative firewalls. They're decently clothed with an event horizon. They're not naked firewalls of this kind, right? So you will.
Well, I mean, if they're eigenstates of the radiation field, then they would be. I'm just saying they would be naked.
Well, I don't want to speak for them, but I thought they had an argument that the outside really looks like a thermal atmosphere, and you know the firewall is not so easily observable from the outside. But I won't speak for them.
I agree. David will eventually tell us ways. Just let him go on.
Okay. Okay, so what I'd like to talk about now is to think about forming a black hole from smooth collapse. And if we're in the post-page epoch, we could still imagine computing this expectation value by estimating corrections to this exact thermality of the outgoing modes. So let's try and do that. So we have some kind of local probe near the horizon, and that'll have access to some relatively small subspace of the outgoing modes. So if we place our probe very close to the horizon, then most of these modes will have been very recently emitted. We'll call this subspace of the radiation A. And in this post-page epoch, that'll be maximally entangled with the earlier radiation R. And we'll assume that's well space-like separated from A. Okay, so let's try and compute this distribution function for these outgoing modes. So we essentially have a pure state on this Hilbert space, A times R. We can construct a reduced density matrix. So if we're doing a measurement near the horizon, according to Einstein locality, we should just trace over the space-like separated Hilbert space to define this reduced density matrix for the A modes, or the A degrees of freedom. And we can expand that if we want in terms of some energy eigenstates or energy density matrices for that live in the A space with some coefficients. Okay, so if we have a complex pure state, so some kind of state where we have a lot of entanglement between A and R, there's actually a nice approximation scheme for computing these corrections in a limit where the entropy or the dimension of the Hilbert space of R is much bigger than that of A. Okay, so we do this by integrating over the possible unitary transformations that move us around on this high dimension Hilbert space. So when we do that, we get this answer. We get some large dimension of Hilbert space dependent factors. We get some normalization of the total dimension of the Hilbert space and some very small corrections. Okay, so let's process this a little bit. So both the radiation and the very recent radiation were in thermal contact with our stretched horizon. So most recently, we're thinking of A in the stretched horizon as evolving unitarily, which essentially makes ds dA ds dEA equal to ds sub B ds EB, if B is the stretched horizon. And one can make the same kind of argument a little bit before for when the last bit of the earlier Hawking radiation was emitted. And between those two times, this temperature isn't really going to change very much. So to within small corrections, both of these terms have the same effective temperature. So T is the adiabatic Hawking temperature of the black hole at that point. Okay, so we can Taylor expand this function. Expanding in inverse powers of the entropy of the radiation. And if we put all that together, we find that this reduced density matrix has this almost exactly thermal form up to corrections that are of order e to the minus the entropy of the large system of outgoing radiation. Okay, so maximal entanglement of A with the much larger system and being able to trace over this much larger system kind of saves the day for us. And if we plug in and compute the stress energy tensor, we find it's actually suppressed by the exponential of the entropy of the outgoing radiation. Okay, so it's essentially tiny on the stretched horizon, and we get no kind of naked firewall. Okay, so I would view that as a success for black hole complementarity. We've essentially shown that if you have one of these radiation eigenstates, it's not the relevant state for computing what a local infalling observer sees as they cross the horizon. Okay, any questions on that? Okay.
Well, I will just, you just used the words as they cross the horizon. I think you meant as they approach the horizon.
Well, they can get up to the stretched horizon, yeah. They can even cross the stretched horizon. Okay. I'm not sure I know what that means, but
it sounds like you may be saying something more. Let's at least try on that. That you're saying if you look at the stress tensor from the vacuum fluctuations just outside the horizon, there's some averaging that makes those smaller than you might have expected.
that's right. So every eigenstate in this outgoing Hilbert space produces a much larger expectation value for the stress energy outside the horizon than you see when you actually do this tracing over a complex pure state. Okay, so since no one's going to object to that, let me.
This tracing is done automatically as you do the computation, right? So if you just observe it. Yeah.
So also, if you projected on a definite, state of, I guess you called it, of R, then you would not have that cancellation. So you're saying it's a feature of this average over.
That's right. Okay, so, let me raise some objections then. So, if you were to measure this early outgoing radiation, you could imagine projecting the black hole into some NR eigenstate and then asking what happens as this infuller approaches the horizon. So in that case, you might expect the infuller to see the horizon, or perhaps not. Or you might even argue, if you don't measure the radiation, decoherence will kind of do the job for you and project you into some kind of essentially an eigenstate of NR, because I guess one of the slogans of decoherence theory is that local interactions abhor non-local superpositions. And what we're concluding is we have to average over macroscopic superpositions of different kinds of Hawking radiation in order to get rid of this firewall. Okay? If you want to have some kind of local superposition or local eigenstate of the outgoing Hawking radiation, you're going to be in a situation where your outgoing state is very close to one of these NR eigenstates, and you're going to see a firewall outside the horizon. Yeah.
So I've heard this kind of before, but what confuses me is that in principle, we're just talking about the matter that collapsed to form the black hole and the space around it. When we talk about decoherence, there's always an ancilia or some other system which will entangle itself with it. Here,
yeah.
In principle, of course, when there's a black hole, there's stars around and all that. But in principle, there's only the black hole and the space-time. What is causing this decoherence?
Exactly.
No.
Oh, I'm going to talk more about it. Okay. Good. So, well, to try to illustrate some of the potential confusions, let me try and confuse you about the EPR paradox. So let's imagine we have a spin singlet. So we have some kind of tensor product running horizontally and a sum with a minus sign running vertically. So this is supposed to be a picture of a spin singlet. So, and we have Alice and Bob at space-like separations ready to do their spin measurements. Okay, so as came up in Herman and Eric's talk yesterday, if Alice makes a measurement, she will detect spin up or spin down with probability 1/2. Likewise, Bob will measure spin up or spin down with probability 1/2. So nothing too surprising there. It gets a little more perverted, though, if, say, Bob makes a measurement. Let's say he measures spin up. And Alice declines to do her measurement, but then moves up into the causal future of Bob's measurement. Let's see. So now when Alice makes her measurement, naively it seems like the rules for probability have changed. She now does her measurement and with unit probability finds spin down. Okay, so there are different ways of thinking about this, and I guess that's the interpretation in the usual Copenhagen view of things. You could also work on some kind of big wave function that includes Bob and Alice. And even then, if you do that, then even then the rules up here for Alice making a measurement are the same. She'll measure probability up or down with equal probability, but at the same time she will move onto a different branch of the big wave function and see agreement with Bob's measurement. Yeah.
Yeah, I just had a question. You were saying that Alice has to wait with doing her measurement until she's in the future cone in order to have the perfect correlation. But I thought she could just do the measurements at a space like separated. That's obviously where the EPR paradox is coming from. That space-like separated measurements still can have correlations. So she doesn't need to wait until she's in the future to do her measurement. Right?
No, she doesn't need to wait.
So
I'm
she
saying
can do it earlier.
if she waits. So if she doesn't wait, then she, I said at the beginning, she measures up or down with probability 1/2.
No, but it's still if she would do the measurement at the same time as Bob and the two are space-like separated, then if later on they compare their measurements, they always find that it's consistent, regardless of whether they did it when they were.
That's where these confusions start to creep in.
You mean that she has received a classical message at that point from Bob saying that, okay, now if you go and do the measurement, I already can tell you what the outcome is?
Yes, that kind of thinking. So one has to be careful in viewing measurements versus the kind of, well, I guess you could phrase it as correlations. So the kind of local measurement that either of these observers do gives up or down with probability 1/2. But once you get into computing those kind of conditional probabilities, which only become relevant once Alice moves into the future light cone of Bob, it seems like the rules for computing probabilities change. So let's think about this in the context of the pure state black hole. So if we imagine this corresponds to some measurement of the distant Hawking radiation, then it's possible for, if you're dead set on computing one of these conditional probabilities, it will be true in the future of such a measurement that your correlation function will change, and it will then be given by some kind of eigenstate of the outgoing radiation, and you'll then see this very clear firewall outside the horizon. But if you're doing a local measurement at space-like separations, you will, by the same token, not see this firewall.
I either didn't understand or don't agree with that last statement. I'm confused. You're supposing that someone far away is doing a complete measurement of this thing you called R onto the, say, number eigenstate basis.
Yep.
Somehow they're doing that. Okay. And you say that even though that is taking place, you can have an observer who follows through the horizon or up to it and sees just the average result and is not decoherent by this distant measurement.
Yes, so if they're doing their measurement at space-like separations from the measurement, this argument will apply.
Yeah, the thing is, I don't think it has anything to do with space-like or time-like. If Alice receives the piece of paper from Bob saying what Bob's measurement was, and she decides, oh, I'm not going to look at this, I don't care what Bob did, and just does the measurement, from her perspective, she sees exactly the same thing, whether she's time-like or space-like to Bob. So I don't think it can be the case if Alice is jumping into a black hole, that if she looks at a piece of paper, she gets burned up, and if she doesn't look at the piece of paper, she doesn't.
Yeah, that is not what I'm saying. Yeah.
I might expect a different problem, I think. Namely, again, if we think about sailing across the horizon and why you're conventionally allowed to do that, it's because you have this precisely correlated state of the just inside and just outside modes that's where there's a cancellation that takes place in your interaction with those modes. And so you're saying if I look at the outside stress tensor and instead all of the modes are correlated with the past radiation, there's some averaging that makes that all smooth out to not be as bad as I might have expected. But then you've also decorrelated the inside modes with the outside modes.
Modes.
Well, sorry, you don't want to think about them, but a lot of us here do. And so all of the inside modes are now decorrelated with the outside modes, and so you might have still the same problem, a firewall basically just inside the horizon, if you look at the stress tensor of those modes which you've decoupled from the outside.
So, well, yeah, in the setup I've been describing, I only have effective field theory outside the stretched horizon, so I'm not going to touch that. We heard a lot about it yesterday, but I've already shown that if you have an eigenstate of this outgoing radiation, I mean, you already see a firewall outside the stretched horizon. There's no reason for it to hide behind the global horizon. So it's something you can already address using the kind of effective field theory that everyone agrees on without having to get into these more advanced discussions that we heard about yesterday.
So at the level of 2 qubits, I think the firewall question is that you have to do a Bell measurement on both qubits to see or not see a firewall. What you're describing is doing a measurement on 1 qubit. So that will,
yeah.
I mean, I don't think it's supposed to show a firewall or not. The firewall question is a Bell measurement on both the qubits.
I disagree. So I would, well, a firewall for me would be a quantity you can observe in a one-point function. So as I've said, a local measurement will correspond to tracing over whatever measurements are being made over here. So if Bob does a measurement of the spin, what Alice is really going to be doing then is tracing over Bobs that are some of which who have measured up and some of which who have measured down. And in doing so, we'll not see a firewall. That's right. I'm not trying to say anything surprising on this slide. Sorry. Okay, so.
It does have some bearing, though, on the discussion, because by the same token, Alice cannot determine if her spin is entangled with Bob's.
That's
by
right.
A single measure.
Right.
Yeah, she cannot determine if her spin is entangled with Bob's.
Yeah.
So the fact that her spin is in a mixed state is something that she cannot determine by having a single spin.
That's right. Yeah. So that is the point I'm trying to, or one of the points I'm trying to emphasize here. So if we really want to insist that Bob or someone outside the black hole has really projected the system into some eigenstate of the outgoing radiation, it really amounts to just changing our initial state so that we're just working with this initial state rather than the singlet state that we started with. Okay, so let me try and apply that a little more sharply to the objections I raised. So if we have some large measuring apparatus projecting onto this, we expect some kind of very short decoherence timescale because this apparatus is very large. And if we really want to think about what's happening, there's going to be some kind of change in the state of the black hole. And it's essentially going to be equivalent to putting the black hole into some non-generic state for the same reason that the projection of the spin system corresponded to just changing the initial state so that you had a spin up and a spin down. So as I argued before, in that case, you really are going to see a firewall. Okay, so the issue for me then is, if we're trying to form this black hole from smooth initial data, we're not really going to be in one of these non-generic states. And I think one of the hidden assumptions in the firewall story is that this outgoing Hawking radiation is somehow decohering on its own into some local outgoing radiation state. So something close to one of these in our eigenstates. So if you don't use measurement to project onto one of these eigenstates, you could ask, whether this decoherence really works. And, in everyday life, decoherence works really well. If we open the box and look at Schrodinger's cat, we all agree on whether he's alive or dead fairly quickly. And to actually do the computation, you have to think about how we're interacting with our environment and compute a time scale. And for very large people, it's extremely short. So you might ask, does that work for this outgoing gas of Hawking particles? And this is where this free propagation of the Hawking modes away from the horizon kind of comes back to bite you, because you try and compute the decoherence time scale, it's basically infinite. So nothing is really preventing you from having this outgoing set of macroscopic superpositions of the Hawking radiation. So when you then go and compute your expectation value of the stress energy tensor near the horizon, you see no firewall.
Well, okay, I really don't agree with that.
I just showed it before.
Well, if you have a quantum mechanical, maybe I just didn't understand, but if you have a quantum mechanical system and you have outgoing quanta and they just propagate away as a free field and go away, the effects are exactly the same whether or not somebody, from the perspective of somebody left behind by those quanta who doesn't have access to them, the effects are exactly the same whether it interacts with some other system and decoheres or not. Isn't that true? Yeah, okay, well then I must not be understanding the words. Maybe I think somehow they think they mean the opposite of what they mean. But you're saying free propagation of Hawking modes away from the horizon produces an infinite decoherence time scale, and that prevents the firewall?
Well, you could worry that, okay, so you're falling in, you fall through the radiation cloud, and you could somehow worry that your interaction with the radiation cloud somehow decoheres in a basis that is an NR basis. And if that were true, then indeed you would actually be in trouble. But he's just saying that, the information is so diffuse, it picks such a weird subspace of the radiation that when you decohere the radiation by falling through it, you don't decohere it into that basis. That's a non-trivial
discussion. I think Aaron is actually agreeing with what David said, but pointing out that you don't need all the assumptions on this slide, and the conclusion is even stronger, that even if there is decoherence of the radiation far away by some other agent, you still have no firewall.
Well, not if the, well, I mean, if your outgoing radiation is in an NR eigenstate, and you do the computation of the stress energy tensor, you find a firewall. So let me back up. So
who's decohering? Who's decohering this radiation? I still don't get what's the environment.
So here I'm doing this trace, and I'm assuming I have a complex pure state. If I was in an R eigenstate, this would be wrong. If this is wrong, I get a firewall. Well, it doesn't just have to do with that, but I'm choosing not to talk about the firewall inside the horizon. Because I don't want to get into a discussion like yesterday.
Everyone would agree that outside the horizon, what you're saying is you could create a firewall by doing some extraordinary measurement on the radiation, but generic things you do outside would not create a firewall outside the horizon. Maybe I'm sorry, I'm not understanding, but the statement is some generic interaction you had with the radiation outside would not create a firewall outside the horizon. But I thought that most of the arguments for the firewalls have to do with them being just behind the horizon, not just outside the horizon.
So I already showed before this slide that the arguments for the firewall lead to a firewall outside the horizon. If you work in this radiation eigenstate, you see a firewall outside the horizon. Every single eigenstate gives you a firewall outside the horizon. That's the point. But but every basis element of your Hilbert space gives you a firewall, but nevertheless, when you put them in a complex pure state, the firewall goes away.
Sorry, could I just ask a really simple question? Are you assuming that the information comes out in this argument, that everything is unitary?
Yes.
Yes. And is that assumption, that very first line, that you're starting with the pure state on A cross R, so that at every time the radiation near the horizon and outside is in a pure state?
Yes. Yes.
So in your last comment about this basis of in our eigenstates, I assume this is a reference to, for example, the argument I gave in the last week in my recent paper with Joe.
Not directly, but it could be.
You implied it has to do with the firewall argument. So I just wanted to say that an important part of the argument I gave in the first talk of this workshop last week, which you weren't here for, okay, but it was in this paper I wrote with Joe a month or so ago, is that when we look at, we do use in that argument a basis of state, well, I wouldn't even call it basis, but anyway, we use states in which some mode has a definite eigenstate, and those span the relevant states. But it's important in our analysis that we use that to compute the average of a positive definite quantity that can't cancel out, that can't have cancellation between different states. And your calculation, where you look at the stress tensor, is completely different because there are positive and negative stress tensor fluctuations.
Okay.
even more basic, which is there was one argument you gave in your first paper which had to do with creating a firewall maybe outside the horizon, or I don't know, inside the horizon, by doing some very complicated measurement of the radiation. Now, as far as I understand, all the later arguments involve some reference to the interior. Is this correct? I mean,
all of our arguments involve some reference to the interior.
Reference to the interior. So
we have no argument that applies to the exterior.
Well, maybe there's this argument which I think maybe you're addressing, which involves doing a very complicated radiation measurement on the outside, which could create a firewall outside the horizon. Okay, never mind. I agree. I would like to. I just want to.
If the
understand
infaller can manage to do a sufficiently complicated measurement, then you can see it. Then they can see a trace of the firewall outside.
Right, but I just want to understand if you're addressing that argument, because if I understand correctly, all the other arguments involve some reference to the interior. So unless you make some reference to the interior, I find it hard to see how from an argument of this kind one could exclude a firewall that exists just behind the horizon. Which I think their arguments don't lead to firewalls only outside the horizon, but firewalls that could be just behind the horizon.
Okay, well, I disagree with that, but for reasons I've explained. But that's what. One can take all these ideas and apply them to a particular model that reconstructs modes inside the horizon. And again, all the conclusions will largely carry over that as long as you're allowed to trace over these modes, and as long as you're in a complex pure state, then this kind of structure will still emerge. And these extremely small corrections to what would have been an exactly thermal state, and I think everyone agrees that the Hartle-Hawking state does not have a firewall, they will, again, suppress the presence of any firewall. But
there are arguments about this operator that looks like it's positive, for which it's hard to get cancellations by summing over large numbers of. I don't know.
I don't want to get into that, but okay. So let me conclude then. So, okay. So what we seem to end up with, which perhaps at least I find surprising, is that the Hawking modes are really in a macroscopic superposition. And no one else seems to be worried about that, but let me say why this is useful. Just to conclude, I've argued that black holes formed from some smooth initial conditions produce no visible firewalls. And this is a nice test, I think, that black hole complementarity passes. So what we have in the outgoing radiation is some non-decohering macroscopic superpositions of these outgoing states, which are an important part of this story. And if you want to construct interior observers who see local quantum mechanics, this is really a prerequisite, because you can't have the same state describing that decoheres with respect to two completely different Hamiltonians. So if you want your interior observers to see ordinary quantum mechanics, they're going to be viewing this state from the point of view of their local Hamiltonian. And they ought to be able to do their Schrodinger cat experiments and whatnot and have ordinary decoherence. One of the ways of phrasing the firewall problem is that you can't have two Hamiltonians that are not local with respect to each other decohere the same state. So this, I think, this observation, I think, opens the door to having a conventional interpretation for these interior observers, because I feel like we were missing this point, that there actually is no natural mechanism for decohering these outgoing Hawking states. And we end up with some complicated macroscopic superposition, which we're totally not used to dealing with in our usual view of measurements. Yep.
In the real world with real black holes, these excitations will go out and they'll scatter on things. They'll scatter on the microwave background and various other things. And so, and in fact, that's going to produce decoherence ultimately. There's some time scale. You can try to estimate what it is. So I don't see how you can assert that you don't have decoherence. Don't know what basis exactly it decoheres in, but it does by those mechanisms.
That's right. So I kind of already addressed that point before. So if there is some operation that changes the state of the black hole into an eigenstate of the radiation number operator, then it's possible to
well, I don't know what
get it into a non-generic state that sees a firewall.
I don't know what state we get it into by scattering off of all of the stuff it'll scatter off of, but it is going to have the effect of decohering it, and so that contradicts your third line, that it's non-decohering.
So this slide kind of deals with that issue. So if the measurement is space-like separated from the point at which you're doing the observations, there will still be no firewall, because you'll still be tracing over the different outgoing superpositions.
I think what's a critical reason why you're part of your argument here is that from the perspective, you're only looking outside the horizon, and as Alice comes in, if she's just measuring the near horizon system, for you, whether or not there is a firewall does not correspond to a linear quantum operator. You're basically saying there's no firewall if it matches the Hartle-Hawking state outside, but the Hartle-Hawking state is a mixed state. And so
I'm
there's
just
no
computing the expectation value of a linear quantum
right,
operator.
but as Don pointed out, that can be positive or negative.
Sure.
And these things can cancel out. In regular quantum mechanics, if you have two disjoint systems, there's no way that somebody measuring one disjoint system can kill me in the other disjoint system.
I completely agree.
The expectation values of what I see. If they measure something weird, if they get an atypical result, that could have implications for what I see. But if I just know they made some measurement and got a typical result, it doesn't change my expectations.
That was something I was trying to explain on one of the earlier slides, but I guess it didn't quite work. But if you then go into the future light cone of that person who did the measurement, then there is this sense in which one can compute conditional probabilities where the rules change.
I certainly agree you can compute conditional probabilities and that you can see entanglements in that way. But if we're just talking about distant Hawking radiation, I don't see why the conditional probabilities matter. Say Alice only cares whether she dies.
I agree. That's my answer to Steve's question. Okay. Well, that was it. Thank you.